a deep energy retrofit. What is a deep energy retrofit? Why do it? Maybe why think twice about doing it? Some of the reasons that we talk about energy savings versus embodied carbon and the reasons why we started developing HP panel. And then Liz is going to walk you through an actual case study of a project that she has worked on. So I will go from there. Next slide. So I apologize profusely if you live in Alaska or Hawaii, or if you're from there. I did not quite get that on the slide, but this is a problem that I know you are all well familiar with. Probably most, if not all of you, know that residential and commercial buildings consume 40% of the energy in the US and about 75–76% of the electricity. I'm sure you know that the older buildings tend to be the greatest offenders, and they really only started looking at energy code and energy performance in the 90s. So most of the buildings that are 40–50 years old are not performing well. And of course, the much older buildings, frankly, may have no insulation at all. So all of us have been tasked with a significant reduction of building energy consumption. We are all on board and understand that there are national climate goals and that we as designers are part of a national conversation. And I think most of us understand that there needs to be some kind of innovative, cost-effective technology that will make it a lot easier and less expensive for people to access improved energy performance. And while there's a lot of options out there, I don't think any one person has come forward with an easy and quick solution. Next slide. So with every problem comes an opportunity, and people have been talking about this market opportunity for 20 years. I found an old AIA report that was talking about the great opportunity, the market that's expanding for decarbonization. And if someone asks you or someone asks me, what's the size of the market and the opportunity, it is literally all over the map. All that I can tell you is it's big. I think with some confidence, I can tell you that there's between 10 and 16,000 triple deckers in New England. And beyond that, all of my data sort of starts to go south. If you just run it through Chat GPT, you're going to get varying numbers that kind of hover in the billions that are growing from 1 to 6 in the next 5 years. If you look at the Rockefeller Foundation, they will tell you that there's about $1 trillion in savings to be gained in the next 5 years. That translates into a $279 billion market. I'll let you read the rest, but the point is it's big. If you look at the country and the climate zones, it isn't going to be the same for every region. The hot, humid climates aren't going to be as interested in the insulation solutions as the northern climates. The northern eastern climates may have the bulk of the old building stock. Particularly right now, we're talking about multifamily and kind of mid-rise. So the map is just telling in terms of showing you that there, again, the solution is going to be varied per region, and there are going to be different concentrations of different building types depending on kind of what market you're in. Next slide. So what is a DER? What is a deep energy retrofit, and where did that come from? The Dutch Energy Sprong Consortium was really the first people that I knew that started talking about it. They were talking about renovating existing housing to net zero energy. They wanted to make sure that occupants were comfortable and healthy, and they wanted to figure out a way to finance this. So one of the things they started looking at were future energy savings as a means to finance current renovation. And the other stipulation that they put on it was that this renovation has to be done while people are still in the building. You cannot expect everybody to move out for the duration. So you should probably be able to do a sort of a recladding turnover in about a week, which is a huge ask. A big difference between the Energy Sprong folks and here in the US is that we don't have large housing portfolios. Housing does not tend to be government run or government owned, and when it isn't usually uniform. So the idea that you might be able to come in with a massive panel, kind of mega panel overclad, might not work as well for us as it has been working in Europe. So the GSA has a slightly different definition of what a deep energy retrofit is. That is a building renovation that reduces on-site energy consumption. It used to say 50 and now it says 40%. It is a whole system approach. It doesn't just look at the exterior, which Energy Sprung doesn't either. There's an assumption that you're moving onto electrification. And we do assume in this country that you're monitoring performance, that it's not just one and done, but you actually have to demonstrate over the life of the building that it's still working. Certainly, we have had government step in with both carrot and sticks. There's Birdo, for those of you that are familiar with Massachusetts, and New York has a similar one that asks that large buildings be net zero by 2050 or begin to pay a sort of a penalty tax. There are also carrots. There are programs like Lean and Mass DOR that are offering significant incentives for decarbonizing housing. So there is a lot of chatter right now. There's a lot of energy, excuse the pun, and innovation around doing deep energy retrofits. Right now, the effort is primarily focused on housing stock. Housing does make up the bulk of the building square footage that we have in the country at the moment. Next. So there are good reasons to do it, and I won't belabor these because I suspect if you're on this call and part of this group, you're on board with understanding that having a good R value on your exterior and a tight envelope is really the best way to go. That you can electrify the buildings, which is great, but if you don't reduce consumption, there isn't going to be a way that our grid can handle that much more drain on the grid. So it is really both and in terms of the optimizing the systems and then making sure the building envelopes can stop the leakage so that we don't use more heating or cooling than we need. And you could further sort of move toward net zero with on-site energy generation. And that was really kind of where we came out of the triple decker challenge competition with, was that the only way to make this financially viable for an individual building owner was to allow them to add on to the building so you would increase the property value, also generate electricity, also kind of combine it with their neighbors so that they could potentially sell it and tighten the envelope. Otherwise, it just turned out to be a very expensive venture. And we'll talk a little bit more about that when Liz does the case study. Lowering energy costs is better for renters because they have lower expenses to pay. And then again, there's a greater benefit that if 90% of the buildings of 2050 are already built, we would all do well to actually lessen their energy consumption. So why not do it? Because it seems like it's sort of a no-brainer. Well, if you go to the next slide, I think every good idea has its detractors. And Michael Angel of the Green Home Institute has been one of many people to sort of be a bit skeptical, saying that are really these deep energy retrofits a pot of gold at the end of a net zero rainbow. And I think there's some truth to that, that to do a really well done deep energy retrofit can be incredibly expensive, and the perfect wall is not the same for every building, and it can be really hard to achieve. And as I mentioned earlier, the return on investment can't just be calculated by the lower energy bills. There are also other costs. There's actual carbon costs that, depending on how you choose to deal with this. There are concerns about what you're using in the deep energy retrofit. So foam, mineral wool, fiberglass, those have pretty significant embodied carbon concerns. PVs are largely made of silica crystals that are expensive to mine, tend to come from China and Russia, and the processing of them is not a terribly green process. And then there are other things, like, is a tight envelope in an old building necessarily a good thing? All of those things I think could spawn large discussions, but it's just to say that, kind of for every thought about what we should do, there's a debate about how we should get there and is it really the right answer. Next. So in the interest of time, I am going to move toward incentives. So Mass CEC and NYSERDA are kind of two big movers in this space in our region. I think NYSERDA has really put a stake in the ground nationally as being one of the most progressive organizations. That's the New York State Energy Research and Development Authority. I think that's what it stands for. And they have invested a lot of money in decarbonization. They've partnered with the city of Ithaca to become the country's first zero carbon city. Ithaca only has 30,000 people in it, so it's a good place to start because it seems like it's a sort of solvable problem and maybe a good case study. But there's lots of opportunities for people that are interested in pursuing this. There's money available, there are grants available. The HP Tech arm of Westwork is completely grant funded. All of the work that we've done has been around raised funds that we've gotten from Mass CEC. We haven't actually gotten anything from NYSERDA, not for lack of trying, or from the Department of Energy. So here, next slide, here in Massachusetts, there's other opportunities. There are RFPs for the actual triple decker pilot project, not just for low income, but also for market rate. There are RFPs out there to come work with the housing authorities on plans for decarbonization. So there's money available and there are people asking for help. So if that's a space that you're in, you're probably well aware of some of these things, but there are lots of incentives to do it. There are lots of people that are trying. It's a very exciting time to be in this space, but it is challenging for all the reasons I laid out. Next. I'll move very quickly through HP panels. So again, having emerged from the triple decker challenge, we had a little bit of prize money and we used that to develop some prototypes. We were borrowing some space at a fab lab out in Waltham. We parlayed that into a grant from the state of Massachusetts with Mass Ventures, and we were able to get some space over at Autodesk. We wrote a residency application and we were accepted. So first year we were kind of out in the field. Mostly we were playing with foam and low cost materials we had on hand. Second year we had some money from the state and then later from DOR. We started developing prototypes. We started shooting for targeted cost per square foot, about $10 a square foot. And we moved away from foam and we started using wood fiber panel, which is very common in Europe. It is not terribly common here in the US. Nobody actually makes it yet, but there are people in that space, notably Timber HP out of Maine, that we hope will soon be producing the board. We can come back to this if people have questions, but I just want to make sure we have time to cover everything. Next. So one of the hardest things to do in a deep energy retrofit, or actually not a deep energy retrofit, any overcladding project are dealing with the transition details, or dealing with the windows, or dealing with the corners. So we spend a lot of time with that. Our system is a snap-in system as opposed to a built-up on-site system. And that's largely been due to kind of failing at coming out with quick and cheap details that can be installed easily. We've moved towards much more towards an IKEA-like kind of system of components that don't need a lot of tools to install. And we've been working that out at Autodesk for the last year. Next. Again, this is sort of back to the boards. We keep coming back to different ways to deal with the corners. It was a lot easier to develop the panel itself than it was to develop the hang and transition system. So we're well into that. We've done a lot of prototypes. We're still working on that. And we'll carry that forward. We're writing another series of grants, so we're hoping that we can move towards a little bit more of an industrialized fabricated approach. Next. So the current state of the market, if somebody asks you to do an overcladding project right now, and we have some in the office, what are you going to look for? You're probably going to look for a product that uses foam insulation. There are a number of people that make a panel product now. You can probably count them on one hand, and almost all of them will be using foam. Some of them will look to use a mega panel, but most of them will do a built up on site. So as I mentioned, we're trying to move away from that to a system of smaller parts that are more easily handled, that need a little bit less skill to install. And we really want to keep the product carbon neutral. So that those are sort of the goals that we're trying to hit. Next. We've had great fortune. If you ever have the opportunity to do a work project down at Autodesk, you should. They have every tool that you might imagine. We have very much enjoyed their superior CNC technology. We've been vacuum bagging our product. We've tried a bunch of different coatings. We tried fabrics. We tried cement. We are currently working with the breathable epoxy. Next. And we are also running simulations in hopes of moving towards manufacture. We're obviously getting a little bit out of our depth as architects and contractors, so we are working with some consultants to try to figure out how this could actually be manufactured off-site and largely automated. So again, this is all in an effort to keep the installation costs low. We believe that if we can't get a low installation cost, that it won't happen. So, and I think Liz's case study will help you understand why. Next. So again, I'll sort of start to wrap it up here, that what we've been trying to do is to develop a process which starts with a 3D scan of a building that gets all the information, that tries to optimize the panel layout as specific of the building, and it's customized to the building, but at the same time, it has to be made up of component parts that are pretty regular. Otherwise, it's going to be very expensive to do. We are moving into a phase next year where we're going to hope to go back outside and monitor it in a building to see how it performs. People are very concerned about using these bio-based products on the outside because they do tend to hold a lot of water. So it's up to us to demonstrate that this is a workable solution. Next. So finally, just where did we start? And again, this is much more about HB panel than it is about Westwork. But in 2021, we were outside doing mock-ups, kind of doing a sort of working out of the back of a truck. 2022, we moved over to Autodesk and had some climate controlled prototypes. And in 2023, we hope to go back outside, put this back up on a triple decker and then monitor it. So hopefully I'll be able to come back to you in a year's time with some more positive data. And with that, I am going to turn this over to Liz.
Thanks, Katie. And thank you for the kind words at the start of the presentation. So to introduce myself, I'm Liz Haver. I'm the head of the energy design team here at Westwork. I received my Passive House certification in 2020, but my passion for energy conservation really started in 2018 when I joined Place Taylor, who specialized in passive house construction in Boston and really pushed the envelope, pun intended, in that sector. So I kind of brought what I learned there, and I'm bringing it here to Westwork to help apply it to the team and make sure that all of our projects do incorporate energy modeling to some degree, and that we're hitting these energy targets that we're defining early on in a project. So I'm going to walk you through a case study that I did. This is, I'll go over the goals of the project, then the design approach, and then I'll end with some operational cost comparatives. This specific case study I have for you all today will take a different approach, probably a more time-intensive approach to achieving a DER in comparison to a panelized approach like Katie was covering. However, I wanted to offer a comparison to you all. This project here is a total gut renovation of an existing duplex in Somerville that was originally built in 1885, so it's rather old. The clients wanted to convert the units into a single fam residential in addition to achieving a zero energy building and passive house certification. So pretty large goals to fill here. Do note that the project size is quite large for a single family at around 3,700 gross square feet. So achieving passive house level and net zero is going to be hard just due to the volume of the building and the envelope size, because it's more space you have to condition and more envelope for you to lose that conditioned space through. However, even with these potential challenges, the project was awarded Passive House Source Zero Design certification in 2021. This project will wrap up this coming spring, which we will submit for final certification, and fingers crossed we will receive it. The team for this is a partnership with New England Design and Construction. They're the architect and contractor who are designing and building the project. The FIAS rater is Advanced Building Analysis. They're located out in Amesbury, Mass. And then lastly, CPHC was a combination of Place Taylor, and then it transitioned over to Westwork. So these are some of the standard goals for the project, which included occupancy comfort, resilience to extreme climate events, system update and electrification, robust thermal and air barrier updates, and 100% operational carbon reduction. And the image to the right is showing the basic zero emission building guidelines that were published through the Mayor's Office of Housing back in 2020, back when it was still known as D&D. If you're not familiar with it already, it's a great resource for designing low energy buildings, and I do recommend referencing that. The principles shown here, such as continuous insulation, air tightness, passive heating and cooling strategies, are all critical components to consider when undertaking a DER. It's not just updating systems, and it's not just recladding or reskinning your building. So with the goals defined, how do we achieve it? It's important to note that the ZEB guidebook was modeled after Passive House concepts, and to get significant energy reductions in a project, it is necessary to design to this standard. Therefore, we set Passive House performance targets, shown in the chart on the right, as our energy reduction goals. The benefit of doing so is that we're also meeting the requirements of FIAS's sister certifications, which are listed below, such as the Energy Star Certified Home, DOE Zero Energy Ready Home, and the EPA Indoor Air Plus certifications. However, design to Passive House standalone doesn't get us to net zero. So to really achieve that, we have to introduce renewables both on-site and off-site. Before I get into the design approach, I just want to give you a sense of the scope and scale of this particular project. So these are the demo plans. And because this is a gut reno and conversion from a multi-unit into a single family, a lot of the building needed to be removed. This is all shown in blue. So the only things that we really kept were the foundation, exterior stud walls, and portions of the roof. Even the floors were removed in between levels to allow for the reconfiguration of floor plans and plumbing. This was largely possible because the existing structure was balloon framed, so we were able to remove the interior walls. Interior floors. So when designing a DER or a passive house, it's important to identify the conditioned envelope. The red line here is representative of our air barrier strategy. For this particular reno, it was best to exclude the basement because it had a history of being damp during springtime. Whenever the snow melted and we got a lot of rain, they would have a moisture problem in the basement. You can see that we boxed in the stair that leads down to the basement, included that as part of the air barrier pathway. We also took a belt and suspenders approach using several air control strategies, which consisted of closed cell spray foam, taped sheathing, and an AVB membrane. This slide here is showing the insulation strategy, which is similar to the air barrier in that we thermally separated the basement from the rest of the home. We used a combination of closed cell spray foam, mineral wool, and wood fiber insulation products. The closed cell spray foam, shown in pink, was used on 5 of the 6 sides of the basement as a means to control any vapor transmission into the conditioned space above. Additionally, it was used in between the existing wall and roof framing cavities to help achieve a superior R value. We found this also helpful in mitigating any hydrothermal concerns that we were finding in the existing structure. So this here is a more zoomed in detail of our wall to roof connection. We used specific products here for the for the air barrier. It's sheathing that's taped at all seams, and we use the Sega Maves 500 as a secondary air barrier. And we use the spray foam, as I mentioned, as the last line of defense in between our stud cavities. So the thermal updates comparative to the existing stud wall, which was an R12 for total insulation value, the new wall achieved an R45. So it's about a 3-time increase in insulation. Same for the existing roof. It was just fiberglass bats that was kind of falling down from the structure. So we respray foamed in between, going from the existing roof R value of R30 and achieving an R70. The insulation products specifically used are 4 inches of Gutex thermo wall insulation. That is our continuous insulation shown in orange on the outside of the sheathing. And then behind the Gutex, we did a new sheathing layer, which was taped to serve as the air barrier. You can see that's dashed in red. And then inbound of that is the spray foam cavities. Inbound of that, even more so, is Roxel Comfort Bat, where we did an extra cavity on the existing exterior walls. This here is showing a detail of the window install and the wall to foundation detail, which are, as Katie mentioned, are the most tricky details when doing a retrofit. For this particular one, because it was balloon framing, we were able to remove the floor structure between the basement and the first floor, and this allowed us to get it in there and spray foam. So it had a much more airtight seal. So you can see the air barrier again, which is outlined in red, goes along the subfloor sheathing on the first floor, and it goes all the way out to the exterior wall. And again, we spray foamed in that existing 2x4 cavity to really air seal that up and make sure there's no air leakage in there. The windows that we used, we replaced the existing double hung windows with tilt turn windows from Logic. The U value is pretty robust. You get a U of 0.15 comparative to code, which is U of 0.35. So it's a great performance increase. It's also important to note that we want to align our windows with the exterior continuous insulation so that you maintain that insulation continuity. So I'll get into the MEP systems we selected. For heating and cooling, again, we electrified the building entirely. So we selected the Mitsubishi mini split heat pumps and as the main source of heating and cooling. However, for this particular building, our cooling loads were very low. So we sized our heat pumps to the lowest size possible. And to make up for the additional heat demand, we supplemented with the Stelpro baseboard heaters. So you can see for this building, we only have 2 heat pump units, one located on the first floor and the second one located on the top floor. And to really help this air mix, we also undercut all of the interior doors by 3/4 of an inch. And we also relied a little bit on our ERV system to help disperse the heating and cooling. For the ERV, we selected the Zender Comfo Air, which has an efficiency rating of 85%. So it's a very good product. And it's also important to note that when designing for passive house, you have to do a balanced ventilation system. And this is really important because you want to maintain a constant pressure on your interior environment so that you're not driving or pulling vapor-ridden air through your building envelope. We also used recirculating range hoods in the kitchen and condensing dryers. This is really helpful in cutting back on exterior penetrations and the need for unconditioned makeup air. Another alternative for condensing dryers are heat pump dryers. Unfortunately, there's not a whole lot of options on the market yet. But I think if we all start trying to put them in our projects, maybe they'll see the demand and start making more. For the domestic hot water system, again, we electrified everything. So we went to a hybrid electric heat pump water heater. We used the A.O. Smith 80-gallon. However, the runs for it were a little too long, so we had to do a secondary electric water heater on the 3rd floor to accommodate the bathroom up there. All the appliances were Energy Star rated, and all the fixtures were updated to have the water sense certification and were low flow. Because we also did the complete demo of the inside, we were able to replace all the piping. So we switched over to PEX piping and we were able to insulate all of those as well. This cuts down on system loss and reduces internal heat gains. So these are some photos of the construction process. These are lessons learned on site. So I'll start with the image on the left. This is the basement ceiling, and you can see where we have a bundle of cords that are going through the insulation and ultimately up through the sheathing on the first floor, which again is our air barrier layer. So this makes it very hard to seal because there's all these little gaps in between the cords. So for anyone who's going out on site soon, make sure you discuss cord management on site. And the best way to mitigate for this type of scenario is to have them separate and neatly lay out the cords so that way they can seal it properly. You can see in the next image over where those cords come up, they sleeved it. And it's hard to see in this picture, but there is a gap right down here, which when we did the blower door test, I was going around looking for all these gaps and you could feel the air blowing in the house. Another area of concern is high trafficked areas where the tape was getting worn down. So whenever you go out on site, you just want to look for these things and make sure your building is properly buttoned up. The last image is showing a thermal gun that we went around site searching for all these air leakages with. So these are some of the performance numbers for this particular project. I ran a couple case studies to show you guys a comparison. So if we start with the chart on the right, case study 1 is an energy model I did of the existing conditions. Case study 2 is an electrification and a systems upgrade of the existing conditions. So that means I got rid of gas for all the systems. I upgraded all of our appliance to Energy Star and I switched out all of our light fixtures to LEDs. So we did cut down on energy consumption, but overall, because we got rid of the gas use, our electrical bill did go up. Case 3 is both the electrification and upgrades of appliances, in addition to upgrades to the insulation and air barrier strategy. So you can see that our source energy use per person had a 32% reduction between case 2 to case 3. And it makes the biggest impact on our heating demand. So you can see a heating demand is around 56 kBTU per square foot per year, comparative to 8.5 if you also update the assembly. That's an 85% reduction. So that's where you're going to see the most cost savings. The chart to your left is just kind of showing that more graphically. You can see the heating and cooling demand between the case studies. It drops significantly once you insulate your building properly. This is an overview of some operational cost data I pulled together. So the combination of electrical and gas bills for case 1, which is the existing building, you can expect to pay $271 roughly a month. Case 2, if you just electrify your building, you can save $45. But if you also do the deep energy retrofit, you're saving $117 a month. So this is just kind of to show you the importance of insulation for your building as well. And just to point out, this analysis is done without accounting for the renewable energy that was used for this project, because I wanted to show you guys an apples to apples comparison. Of course, if I were to include the solar panels that we installed on site, our electrical costs would go down to almost nil because we covered our on-site electricity use. And that was it for my slides. I wanted to give us enough time to go through some questions.
So Esther or Jeff, I don't know if you want to take over, or do you have people have questions? Or are you just unmuting or raising hands? I don't know if you have questions. That's a lot for an hour, so I'm exhausted.
Yes,
And I put it together with Liz, but please, we're happy to answer questions or let you go eat your lunch.
I actually have a question. I was just going to type it in. But for that, I want to thank you, Katie, in this. That is a very in-depth and wonderful presentation that allows us to have a better understanding of deep energy retrofit. It's for me it's quite amazing, and I was just wondering, well, when you're doing all those upgradings and retrofitting, do you have to handle other conditions such as fire protections or fire hazard that might comes into an old building with triple decker?
Yeah, so we did have to fireproof the exterior walls that were within 10 feet of the property line on the side. So that was handled with 2 layers of gyp for the exterior wall.
I see.
Mm-hmm.
Thank you for letting us know.
You had a slide on the cons of a deep energy retrofit. Did you evaluate those cons against the case study?
No, we didn't. So it's a little bit difficult to do a very straightforward analysis here for a couple of reasons. The case study is a single family home. Liz did some quick back of the napkin calcs and determined that it was about 25% more to do that project as a passive net zero. But even without that, it's a unique project and thus makes it expensive. So when I'm looking at pros and cons on this, I'm not necessarily thinking about the individual homeowner who wants to do a zero energy passive house retrofit. I'm trying to think about it on the scale of multifamily housing. So some of the work that was done in the Somerville case study isn't really feasible for a housing project. So we happen to have a deep energy retrofit in the office now, a large housing project that is managed by Madison Park. It's about 330 units, and it wouldn't be feasible to move all of those folks out and do the level of gut reno that a kind of proper perfect wall, as I was saying, would require. What we're after with some of the research we're doing is what I'll call the kind of pretty good enough solution, which is maybe doesn't hit net zero, but does increase efficiency by 40 to 50%, does move them off of petroleum and gets closer to near electrification. The one area that gets a little challenging with electrification is the domestic hot water, and that just depends on how it's being delivered at the moment. But what we're really trying to do is to come up with a solution that will decarbonize large portfolios of housing in an affordable way. So the expense is a huge one for us, is trying to figure out, I think I'm particularly driven about the carbon costs, but I have to be clear that not everybody is as motivated by embodied carbon as some of us are. That's still quite a debate. What isn't a debate, I don't think, is that we have to find a business model for this kind of deep energy retrofit, or it isn't likely to happen at scale. So if you flip to the next slide, Liz, which is the con one, probably the biggest con again is that the ROI, the perfect wall, the safe, well-executed retrofit can really be out of the reach of low to moderate housing. It's just not a feasible approach. And we're really trying to find one that's a little bit different. I see Nadia has her hand raised. I'm not sure I can you can unmute yourself, right?
Okay, sorry.
Yeah, go ahead. No problem.
I'm just curious, have you done any studies where, what would happen if there was like a week-long power outage in these buildings that have been retrofitted and are much tighter?
Well, that's a really good question, because a lot of them, people have looked at that in terms of how long you can be comfortable, and I don't have that data. Liz probably knows that better than I do. I will say, however, that what you're looking at on this slide was a proposal for sort of district energy. There is sometimes needs to be some sort of supplemental generation for that notion, because the question that you might be asking, or the one that sort of often comes to mind, is if we move everybody off of petroleum and then there's this sort of, we lose power for a month, what does that mean? I don't think anybody has really solved that problem. I have seen, however, studies that show how long a highly insulated envelope will sort of maintain comfort against extreme heat and extreme cold. Liz, you may know more about data on that. I don't have it handy, but I have seen it.
Yeah, I also have seen that, Katie. I don't recall the resource that I read it from, but anecdotally, I have read that code minimum buildings will typically reach the temperature swing outside at around 8 hours, and then a hyper insulated structure will retain the interior comfort for much longer, say 24 to 48 hours. So that might be enough time needed for the grid to come back on power.
Part of the curiosity for me is thinking about if there was a storm or something where power goes out for a week, are there going to be moisture issues in the building and that are going to be hard for either the homeowner to identify or rectify, or if maybe there aren't any, I don't know. That's just something that's always no one seems to address it, and so I'm curious about it.
No, I actually think that's a huge, I didn't go, if you read this whole article that that Michael wrote, and there's a kind of lot of chat about it, there's a lot of debate about this idea of encapsulating the existing wall. I think I haven't seen a lot of doubt about new builds and sort of building to passive house standards for new. But in these situations where you, unlike what Liz proposed, which is what they did with that deep energy retrofit, is arguably they actually built a new wall. You know, they gutted so much of it and then they re-insulated that they did come pretty close to some sort of quote unquote perfect wall. If you're doing a deep energy retrofit and you start, like say you have a brick exterior, right? And then you close the brick and then you have it in kind of a tight wall. There's a lot of modeling that you need to do around that to see at what point you hit the kind of the moisture. I mean, it's a very valid concern. Liz has done a lot of modeling. I don't know, Liz, you could speak to that, but it's that's I think one of the real points of deep energy retrofits that is worth kind of being not skeptical of, but sort of checking and triple checking.
I don't have too much more to add there, Katie. That is a very good concern to have, and I haven't done much research into it, to tell you the truth. But I do know a lot of double stud wall constructions that we do for single family passive homes. We always include a vapor retarder right behind your gypsum wall. So that's going to reduce the drive of moisture from your interior environment into that wall assembly. And I have to imagine that would help slow down the rate if your interior condition were to lose power as well.
Yeah, I think the questions being raised just again underscore the you know, again, I think Michelangelo's being a bit of like the bad boy of the green world, but you know, his point is sort of well taken, that there isn't a thing that we're all going to find that is just going to get us to net zero easily. Every building is different. Climate zones are different. Wall types are different. I think that, you know, again, there's some things I think we can all agree on, which is to sort of move away from petroleum products. But then after that, you know, should we use foam? Should we not use foam? I mean, you know, arguably foam can deal with some of these moisture situations better than maybe wood fiber can. So, you know, these are the conversations that the HP timber people or the HP tech people have all the time, but we keep coming back to the wood fiber because we do think it performs better and that ultimately the kind of carbon cost of it is lower. It seems like you probably are out of questions, which we get to go early, which is good. Everyone likes the gift of time. I know I do. Both Liz and I would be very happy to follow up if you had individual questions. I think people approach this at a variety of levels of expertise, or kind of wanting to sort of nerd out with the quants versus really understand it. I come at it maybe with some of the challenges of the aesthetics. Liz is much smarter than I am about dealing with the performance issues, which is why both the HP tech people and our Westwork people really rely on her. But in addition to the importance of the sort of high performance wall, I don't think people will do this if it isn't attractive. So we really do struggle with again, the making it look at least as good as the historic material that they have on there, because again, it needs to be both cost effective and reasonably attractive. So with that, I will say thank you and very willing to answer further questions if you want to follow up by email. So
does anyone want to talk some more about the insulated fiber panel? Is that possible?
Oh, I'm happy to if you have questions. If you're addressing it to me, do you have? I mean, again, this is a bit different. We wanted to pair these two things together because what Liz has done is actually delivered it, and we are pretty far from delivering it. We recognized a challenge with the triple decker that we didn't think anybody who owned these buildings would do this upgrade unless they had sort of just scads of money. That we felt like if you were just going to do something to move to electrification and then develop an insulated cladding material that was inexpensive, so that you would sort of have a choice: do I do hardy plank or do I do HP panel? Do I do this timber board? We have many, many iterations of this prototype. We started with foam, we started with mega panels, we started with vertical panels. We have come to this after several years of prototyping. We have a couple people who work on this full time, and again, it's completely grant funded. And then myself and Evan Smith, formerly of Place Taylor, pretty much volunteer on this one. Being at Autodesk is a great bonus for us because that's one less thing we have to pay for, and we have access to tremendous equipment and even some testing material. We also have a partnership with Oak Ridge National Labs doing some testing as well. Liz is doing some testing for us. You know, I never imagined myself as being sort of a panel manufacturer. I keep hoping I'm going to get a phone call from somebody like WR Grace, which is like, we'd really like to buy your panel. And I'd be like, yes, because I don't really want, you know, I never imagined us sort of manufacturing panels. But we do think that we've got a good idea in terms of how to keep the cost down with an attractive and green solution. The big problem I have right now is that not enough people make wood fiber panel. Liz showed you the Gutex that they use at Somerville. Gutex and Steico have the majority of the wood fiber panel market. They're manufactured in Germany. Nobody in North America makes a suitable product yet. The Opal folks out of Timber HP that are up in Maine have started developing the wood fiber insulation, and they will eventually produce a board. You know, again, it's really the GoLogic. Those are all the same people. Opal, GoLogic, and Timber HP. They are separate but related and really pushing this forward. So, you know, I would ask you to Google them. You'd learn a lot from what they're doing. And we are very hopeful to work with them, to continue to work with them, because unless people are making wood fiber panel, our really awesome idea isn't going to get out of any further than it already has.
I feel like the presentation covers so much topics that every segment of it can be further articulated. We're wondering if we could have you come back again, Katie, if you don't mind, in these. Hopefully, in the foreseeable future, we can hear more from you, because this is indeed a wonderful topic, and it's perfectly aligned with the issues that we are addressing today with climate change, and we're responding it with, I would say, a perfect solution.
Yes, we'd be happy to come back. Thank you. Thanks for inviting us. It was really this is our, both of us have a shared passion. We come at it a little bit differently, but the more excitement we can get around the topic, as Liz said, I think the more demand will come for it. And that's our hope.
Thank you.
Yeah.
Thank you.
All
All
right.
right.
Thanks.
So thank you everyone for attending. We're gonna close our section 5 minutes early. Thank you for attending and joining SEC meetings. Hopefully we'll see you all next month.
Bye-bye.
All
Thanks
right.
again.
Thank you for having us.
Yeah, thank you. Okay, bye-bye.
Bye.